Okay, so my name is Prewitt. I'm a principal program manager in the Windows and Devices group at Microsoft. My team is responsible for things like StorePort and Spaces and StorePort mini ports, including the NVMe mini port. So kind of to start off today, I want to talk first on the client space, and then we'll kind of talk about data center space. Why is the client different? And then what NVMe features are required? I mean, there's stuff that's optional in the spec, but we really want to be able to use this stuff in certain cases. So talking about why is the client different? Design preferences are very different. You want to do things like save space for things like two-in-ones, mobile, tablet. You want things to be cheap. They need to be elegant, but the price has to be small. So you want to do whatever you can to reduce the BOM cost. The devices have to be hardened against security threats because we've seen wonderful things with people getting their devices bricked by malware, and so how do we protect against that? And then because of all the variety that's out there in this space, we need to be able to have trade-offs between power, performance, things around thermals and stuff like that. And so we want to ensure that whatever we have there can be used in a flexible but elegant way. So, what are these features that are required? I mean, they're optional in the spec. What does that mean? Well, I get this question a lot, and so I wanted to put this one up here real quick. The optional features aren't optional when they needed to buy the HLK. And the HLK is our hardware lab kit, which I think any of the IHVs out here know very well, that they need to run to be certified to run with Windows. And so there are things in there that we say, hey, we're going to look for this, make sure it's there, and test for it, and make sure that the test passes so that we know that the user is going to have a good experience with that device on a Windows machine. So with that, kind of talk through some of these. This is kind of my last slide on the client-side portion. But so as I think we talked about before, boot partitions, we see those as being really important. The idea is that boot device, we can get rid of the SPI-NOR. I know there's ways of integrating it in as well, but from a cost perspective, if we can just use some of that main storage device as the boot partitions in a protected way, great. RPMB is the replay protected memory block. If you're not familiar with that, it's a small piece of the flash device that is encrypted and is protected against things like rollback attacks. That is something that we see as being the ability to get rid of the TPM. The TPM is the costly piece of silicon, which also adds about 2 seconds to boot. So we want to be able to get rid of that and use just the RPMB on the main storage device again. Namespaces is another kind of an important thing. If you can think about it, especially in something like a mobile device, we have stuff that's really meant for the OS, and we have stuff that's really meant for the hardware or the cell modem or something like that. And so there are pieces of the device that we would actually like to hide from the high-level OS and just be accessible either to firmware or, say, the cell modem or something like that. And so namespaces is a great way to do stuff to kind of partition it away securely to protect against attacks and things like that. Kind of an interesting one I want to put up there is what we call drive telemetry. I think Peter touched on that. We're getting millions and millions of devices out there. They all have their internal kind of state that they know about, and gee, wouldn't it be great if we could get back interesting data about what's happening to those devices in the field and get that back to the IHV so they know and can monitor the health of the devices of their fleet that's out there, so that we can improve things for the customer over time. And then on the next one, power management. You think of power management, obviously, hey, this is a great device. NVMe is really performant. It's come down from the enterprise and the data center, but in these small form factor devices, we do have to worry about thermals. So if the device is putting out too much power because it's doing a great job giving us back the data that we wanted, sometimes we need to talk about, say, by the way, let's slow down here and let you cool off a little bit before going on because we're about to burn the user's leg or something like that. And then the one that's we haven't touched on yet because it's not in the spec yet, but it's targeted for version 1.4, and that's write protect. And so that again goes back to some of the stuff around provisioning of different pieces, either of the OS, the firmware, or certain things like I think the big one that I've always been told about is the mobile device, as it goes through the factory line, at the end there's a kind of a quantification of each device, and so there's parameters that are written down to talk about the different antenna matching ratios and getting the best performance out of each of the antennas inside that device, the cell modem, the Wi-Fi, the Bluetooth. And so if those pieces of data are lost, the device becomes a brick. And so we want to be able to put those somewhere on the device and write protect them such that they cannot be done a denial of service attack by some sort of malware. So that sort of thing. So those are the things that are important to us. So I'm going to move on, kind of talk about, we'll shift now from, hey, the kind of the small, thin and light, and we'll talk about big and lots of devices using high performance storage in the data center. So this presentation follows a pretty similar line. It's just exactly like I had before. We kind of say about why is the data center different. You think of it needs to, something like Azure, right? Broad set of applications, different services, different workloads from different users. Today we have over 600 services running in Azure. Bing, Exchange, Office 365, they all have their own kind of how data is read and written across the service. This one is kind of a bread and butter one for us. We need, at that scale and the number of devices that we're buying, we need vendor neutrality, and that's why the NVMe spec is such an awesome tour de force of what we've kind of done around that, so that, hey, everybody's writing to the same command set, everybody's working to the same spec level, and so that allows us a good supply chain diversity. And also globally, because Azure is now in 38 countries around the world. Rapid enablement of new NAND generations. So you can think of this as, hey, the areal density and the RAM of the flash is going up. As we get around that, then the cost per gigabyte is going down, and cost is pretty much our main driver within Azure. So we'll do a lot of engineering work inside the company to be able to move from TLC, say, to QLC and things like that. And this is a flexible enough software to evolve faster than hardware. So as we see these different implementations coming in and doing different things, how we want to react to, hey, the storage as the latencies go down, what do we want to, how do we do partitioning, how do we move different sets of workloads, how we repartition something that's cold to something that's warm to something that's hot. So what do we think are required here? Again, when it's not optional, it's part of our RFP, so a request for proposal. We will actually write that into that proposal to say, hey, we need these features because of X, Y, and Z. And so some of these things, one of the things I think Peter touched on earlier was streams. With streams, we, because of the way that Azure storage works, we try to write up blobs of data together into kind of a container. Each of these containers are going out onto the SSD, and then at the end of the day, that container, if we guessed right, of course, the data in that container kind of goes away at the same time, so we just kind of throw that container away. And so with streams, we can do that in a very clean way so that the device knows, hey, all this data really belongs together temporally, and the idea is at the end of the day, I'm going to trim it all at once in a very clean manner to, again, lower that WAF, lower the entry price for what sort of devices that we need. The next one we look at is what we call fast fail. Fast fail is a feature where if the drive knows that it's either going to take a long time to get the data or that there's something wrong with that data, it should just go ahead and fail the command immediately. And the idea here is that because in Azure we have 3 copies of the data at all times, what I want to do is I want this device to fail fast so I can go look at another device and get that data instead of waiting for that whole timeout time for something to come back with an error. Again, something that Peter touched on, IO determinism. This is very interesting in the sense of each of our VMs that somebody hosts, or that we host and somebody uses inside Azure, has a guaranteed SLA. And so to meet those SLAs, we need to be sure that the underlying storage meets its SLAs. And so IO determinism is a wonderful way to pull in that, 5 nines tail of latency and pull that into a reasonable area so that we know that we're never going to give the customer a bad experience based off of read or write latency time. And again, on this one, drive telemetry. So the fleet inside Azure, actually, if I told you the numbers, they'd probably fire me. But the idea is it's a very large number of devices in Azure already, and it's growing exponentially. And so the ability to gather data out of that fleet and then go back to the IHVs with that data, such that they can improve their devices for that data center experience, I think is very powerful. So, yeah. With that, I did a lot of talk quite fast, but now I'll let Monish come up.